Welcome to the second lecture on the SLAM. Today we're going to cover graph SLAM, and we go through these objectives. We want to understand the SLAM as dynamic Bayes network, factor graphs, and least squares, and show their equivalency under certain conditions. We want to talk about a maximum a posteriori solution to the SLAM and how it ends up being a nonlinear least squares problem. The topic also will enable you to read papers and understand literature. This is the core knowledge in literature and SLAM. A lot of new ideas are built on fundamental ideas that we talk about today. A notation that we will use is weighted norm. I'm going to define it now, so later when we use it, you're familiar with it. You're familiar with the Euclidean norm. A particular notation is when the norm has some weight. This weight is typically, it can be a covariance matrix, then therefore the weight is in terms of inverse of the covariance. Be careful, sometimes in control, the weighted norm is defined using the matrix itself, not necessarily the inverse of it. In this context, we're talking about the inverse of the covariance as the weight, which is the information matrix. Now, one thing that is possible to do is it's always possible to convert this weighted norm into unweighted norm by bringing the weight inside the norm. If you factor the covariance using a Cholesky factorization, because it's symmetric and positive definite, then you get the Cholesky factor L, and sigma inverse will be L transpose inverse times L inverse. And from linear algebra, we know that A times B inverse is B inverse times A inverse. And the notation A superscript negative T is just a way to show that this is the inverse of A transpose or the transpose of A inverse. They're the same. So given this background, we can write down the norm, plug in the Cholesky factorization of the covariance. Then we can see that the new basically vector inside the norm becomes Cholesky factor inverse times the vector inside of the norm. Therefore, this is equivalent to the Euclidean norm when we weight the residual or the vector inside of the norm with the inverse of the Cholesky factor of the weight matrix. Now, the previous one would lead to a weighted least squares problem, but if you apply the weights, this is just the standard least squares problem with no weights. So that's a remark for this notation. Now we're going to start writing our problem. So typically we're going to work with a set of variables. These are state variables, can be position, pose, orientation, position and velocity, and or any other variable in general, just like a state estimation. So the notation X, you are familiar with this. Subscript 0 colon K means a set of all variables from time step 0 until time step K. Likewise, we can define the same notation for the measurements. This notation, it's a joint, it's a set of variables. It's not just one variable. Therefore, when we write P of X comma Z, we mean joint distribution of all of these variables, not just two variables. Okay, this is a set of a lot of random variables, x0 to xk and z1 to zk. So we can use the subscript. And because this is a joint distribution of many variables, we can just separate the first measurement like this. And we can do that for any of the variables. The goal is to, again, come up with a recursive term to find the joint distribution from previous time step so we can factorize it. We did something similar in the Bayes filtering. Here we are keeping the history, the entire trajectory. So if we do that, we can factorize this probability by writing P of zk x 0 to k and z1 to k minus 1. And then the other part will be joint probability of x 0 to k, comma z 1 to k minus 1. From Markov assumption, we know that the first part will be P of zk given xk. Given the knowledge of the state at time step k, we do not need the history. That was the Markov assumption. So we can drop all the terms that will not add extra information, assuming the knowledge is captured entirely in xk, which is familiar to us. This is the measurement model. This is the likelihood model. Times probability of. Now I'm going to separate xk from this joint distribution. What I get, I will get the likelihood model times, again, I'm going to factorize this. So one more time, we can apply the Markov assumption. Given the state at time step k minus 1, we do not need the rest of the variables. Of course, you also recognize this is just the joint distribution at the previous time step. So altogether, we will have the likelihood model times a transition model, which we recognize as the motion model. Whether you show u explicitly or not, there's a known input there. We could keep u as well. It just makes it busier. So for simplicity, we're dropping u. Times the previous posterior or joint distribution. So repeat this for the new joint distribution at time step k minus 1 until you reach x0. If you repeat this process, you can factorize this into a prior term, because at time step 0, there's nothing to condition on, multiplied by this factorized form of the joint distribution, where at every time step I, we have our motion model times the likelihood model. And this is, of course, the same joint distribution. So we can factorize the joint distribution into these modules. And each module is our likelihood and motion model. We know how to model them. We've done it in filtering and in previous lectures in the SLAM. We talked about them. So if we want to show this graphically, using this directed graph. This is called a directed graph or dynamic Bayes network. It is dynamic because the arrows are showing time evolution in the graph. This is not a static. It is always possible to show this graph with an equivalent undirected graph. And that's also possible. That is known as Markov random field, that we don't talk about it much, but that's another way to visualize it. So the factorization we did in the previous page lead to this dynamic Bayes network. So that's the equivalency of this probabilistic factorization and the graphical model representation. When you see this figure, it means the same thing exactly as the written joint distribution factorized in the way I wrote. They show exactly the same knowledge.
So you said the arrows show time evolution. Could you give an example of how they would show time evolution?
The arrows show time evolution in the sense that you are at position x2. Given a motion command, you go to position x3. Right? P of x. No, given, right, so let's talk about x1 and x2. P of example, P of x2 given x1, right? This is a transition model from x1 to x2. And time moves forward. So the arrow shows the direction we move. The arrow from z to x to z means that given that we are at position or the state x1, this is the cause of observing z1. Clearly, we observe z1 at the same time step at x1, right? z2 is not caused by x1. That's the knowledge we see in this graph, and this is called conditional independence. So given any parent, given a set of parent nodes for any node, that node is independent of the rest of the graph. Yeah?
You said that this graph shows the same thing as the equation that we got at the end, where we have P at 0 equals the product of those terms.
Mm-hmm.
How is that the case with this graph? I'm having trouble understanding how that product is implied by this graph.
So the question is how this product of a probabilities corresponds to this graph. This is the topic of probabilistic graphical model. It's a course on its own. As much as we talked about mobile robotics, we could just spend the whole semester talk about graphical models. And probably not even one semester. You can have 2 courses. And it's available online from Stanford. The part that we need is just showing the equivalence of these formulations when you read it in the papers. Very generally describing it, the goal of graphical model is to describe, as we will talk about it throughout the lecture, is to describe the conditional independence relationship between all these random variables. Without this structure of the graph, the joint probability distribution of all the variables we showed, it would never be like the factorized form. The general case, when we have the joint distribution of x0 to xk and z1 to zk, it can be anything. We are not allowed to drop nodes unless we make assumptions, which we did Markov assumption. It is much easier to encode that sort of assumptions into a graphical representation. When we visualize it, equivalent of that Markov assumption, it is captured precisely by the arrows we have and we don't have. The fact that we have arrows from x0 to x1, x1 to x2, and the rule that we read the graph is that given the parent node, the node is independent of the rest of the graph. Then we have probability of x2 given x1, and not probability of x2 given x1 and z1. Because x1 is the parent node of x2, there is no other arrow that is pointing towards x2, therefore x2 is independent of the rest of the variables. This breaks down the joint probability very easily into the product of terms that we wrote down. Without this structure, it's impossible. A more traditional way is to do what we did for robot motion model when we factorized manually by making assumptions and dropping terms, right? Arguably, that's more involved than just visualizing the relationship between variables. So ultimately, when you see this graph, you know how to factorize the joint distribution. For this particular factorization, this is the graph structure. Okay? This makes it very modular and scalable for modeling.
Can we interpret like the measurement is not going to impact the next x2, for example, or x1, z1, and x2 is not going to be impacted by the z1? Can we interpret like that? Because there is no arrow between z1 and the x2.
Now, you need to be careful. The conditional independence, this was background probability we covered, does not imply independence. The fact that x2 is given x1 is independent of z1 does not mean that x2 is independent of z1. Of course, we use x1 to estimate z1 to estimate x1, and that will affect x2. So the conditional independence is encoded in this graph. That does not imply independence, okay? The conditional independence is enough to factorize the joint distribution to smaller terms that then we can model. More practically, at any time step, the robot captures an image, and that image is related to that pose, not the pose at future time step. The image is clearly depends on where the camera is oriented at that particular time. Okay, so these are some examples of terms we can read from the graph. Again, this is a bigger context, graphical models. There are different ways to infer the variables. There are different methods. We are interested in a particular assumption that will lead to nonlinear least squares because that will give us a fast solution, at least locally, a fast solution. We're going to make an assumption. So the assumption is Gaussian noise model. And by that we mean we have a transition model, a motion model. Xi is modeled using some function that describes the motion of the robot. That can be an IMU or a physical model for the robot or kinematics model. Some input plus some noise. And the noise, as usual, is a zero mean Gaussian noise. White Gaussian noise, uncorrelated with itself across time. So the probability of xi given xi minus 1, or we can make it more explicit by adding ui, is proportional to a multivariate Gaussian distribution, dropping the normalizing constant. We can just talk about the exponential part, that is 1/2 of the weighted norm of the difference between the model and the output of the model, weighted by the noise covariance. In other words, the motion model is distributed according to this multivariate Gaussian because the noise distributed according to this model. The difference between xi and f of xi minus 1 and ui is the noise. Therefore, that difference, which we expect it to be centered around 0, if the model is correctly transitioning our state from time step I minus 1 to I, is described by a zero mean Gaussian distribution weighted by this covariance of the noise. Likewise, the way we model our measurement is having a nonlinear measurement model h of xi such that the noise is a zero mean wide Gaussian noise. So the likelihood model is the probability of zi given xi, and that is proportional to the exponential of -1/2 of a norm weighted by the model minus the measurement. So this is a particular way of modeling assumption, but hopefully you are convinced that we get a lot of good results by this Gaussian assumption, although it does not solve all the problems, but usually tends to give nice results to work with in practice and leads to efficiency. So under this assumption, now we can work with more specific models. These probabilities in general can be anything, but now we have a specific model for them, these exponential terms. So next topic is, we're not going to use that dynamic Bayes network. There is a better way to model graphical models. Historically, you will see the directed graph in literature, so it's important you recognize it. But a better way to model these probabilistic models is using factor graphs. Factor graphs are a very general way to model probabilistic problems. In fact, you do not need to think of them as probabilities anymore, but it is related if you want to talk about probabilities. So I'm going to start with an example. Let's say I have this graph. And I'm going to convert this to an equivalent factor graph. A factor graph is a graph that has two types of nodes. Factors are shown by usually black square or circles. They're connected to the second type of nodes, that these are variables. And the factors describes the relationship between variables. Unlike the previous graph, this graph is not directed. So this is a modeling framework. It is more general than SLAM. SLAM is one particular type of problem we are modeling using this framework. So in the context of factor graphs, we are talking about factors or potentials. If I define some potential functions or factors, I'm going to call this phi 0 of x0. This is a function that is clearly placing a prior over x0. I'm going to call these binary factors maybe between x variables as psi. We have another one here. So this function is the same, but the inputs are different. We have x0 and x1. Then we have another one of that type of function that describes the relationship between x1 and x2. Then maybe you have another type, we call it alpha, and that describes x1, relationship between x1 and z1. Maybe another one here, x2 and z2. Now, what makes factor graphs nice is that the joint distribution of all the variables you see in the graph, it is simply captured by the product of all the factors. So once you have the factor graph, you just simply multiply all the factors, and that's the joint distribution. That makes it extremely simple to work with. So the modularity of this framework makes it very attractive. This continues. We have alpha x1 z1 times alpha x2 and z2. So as you can see, the prior factor can be considered as proportional to the probability distribution we had over x0. This function that describes the relationship between xi minus 1 and xi is proportional to our motion model. So the factor that is connecting two state variables is the transition model or motion model. And the factor that describes the relationship between xi and zi is the likelihood. So we have this equivalency, and the choice that we work with factor graph is just a matter of simplicity. It is easier to show all the factors, and the joint distribution is just a product of all the factors. That makes it very modular and suitable for implementing a library like GTSAM. To add a new type of factor, we just need to add that type of measurement model. Once we build this graph, it is clear how to describe the whole problem, and that can be automated. So these are the motivation about this particular choice of modeling, although they are equivalent. So to summarize, each factor is a sensor or measurement model. Graphical model or modeling is an easy way to describe conditional independence and that will enable us to write the joint distribution. Because the posterior is the joint distribution of all those variables. It is very complicated. We need better modeling tools to make it scalable and less painful to track individual terms and how to combine information from multiple sources of sensors. And this seems to be a good framework that gives us a lot of nice to work features. Nice to work with features. Now, given that we can write down the joint distribution, we can talk about maximum a posteriori distribution. In one of your early homeworks, you became familiar with the concept of maximum likelihood, which we maximize the likelihood to estimate the parameter. And maximum a posteriori, when we have prior, then we maximize the posterior. So then we have likelihood and the prior. So when we have the posterior, of course, the posterior is proportional to the likelihood times a prior. We are Bayes rule. It seems to be the maximum a posteriori is the right choice for describing an optimization problem that will estimate the parameter, here the trajectory of the state variables, given data. So one way to solve this is using map estimation. So we want to have the entire trajectory of the robot by maximizing the posterior which is the same thing as maximizing the joint distribution and this is equal to minimizing negative log of the joint distribution. So log is a monotonically increasing function. It will not change the solution of the optimization problem. Negative sign will make the maximization and minimization problem. And in particular, this log will cancel the exponential terms. So we'll make it nicer to work with. And the equivalency of maximizing the posterior and joint distribution, because joint is basically the P of x given z is joint divided by the marginal probability of z. But z does not, P of z does not depend on x, so it will disappear. So I'll add a remark here. So now this is our framework. We can model the problem. We can add as many information as we want across time to model the trajectory from a variety of sensors, as long as we define the factors. Then we form the joint distribution. Then we formulate an optimization problem. If we leave it at this stage, it is too generic. Of course, it is a general optimization problem up to modeling the factors and probabilities. A particular attractive choice is the Gaussian assumption we made that will make all the factors to be an exponential function. The log will cancel the exponential, and we will end up with a nonlinear least squares problem. Then we know how to solve it using Gauss, Newton, or Levenberg-Marquardt. So that will lead to a least squares slam. So I'm going to write this in this page. So now we have a general framework for sensor fusion. So the optimal solution is obtained by minimizing negative log of the joint distribution. And we know the joint distribution is factorized, whether we do it manually or construct a graph, we get the same result. We know the joint distribution is factorized as the product of the prior times all the transition models, motion models, maybe we have m of them, times all the likelihood terms. Now I'm choosing different indices because what if we don't have measurement at a particular time step, or we have motion model? They don't have to be exactly at the same number. So I'm also using xji. So why xji? Suppose zj is a landmark index with j. I need two indexes to know what pose is connected to what landmark. That will allow me to, when I construct Jacobian, I know what row and column I'm working with. So this is the relationship between what pose and what landmark. So let's break down individual terms. Log of the prior, negative log of the prior will be proportional to, because we're dropping the normalizing constant, 1/2 of whatever prior we are placing over our variable. So x0 is the prior, right? X is the variable. Sorry, x0 is the variable at time step 0. X is whatever prior we place for that time. So negative log of the motion model is proportional to 1/2 of the norm squared of the motion model minus xi. So this is adding temporal constraint between two variables in consecutive time steps. And the last one, the log of the negative log of the likelihood is proportional to 1/2 of norm squared of the measurement model and with that we can write down our problem as, again, minimizing negative log of the joint distribution of all the terms that we calculated, because log of x times y is log of x plus log of y. So log, we cancel the exponential, but also it converts the product to sum. This is a multi-objective nonlinear least squares problem. Yeah, I'm listening. I'll explain it in a bit. So we reduced the general formulation to a problem that we actually know how to solve it. You can, whether you solve it yourself, you find an off-the-shelf solver. This is a multi-objective least squares problem. We can set it up and find a local solution to our problem. So one question is why the prior is like that? Well, that means that we had P of x to be proportional to the exponential of -1/2 of x minus x0 squared some prior. I'm treating x as a given measurement here, because x0 is part of the state variable. If you remember, we had x0 to k. You could use different variables, not x. If it's confusing, what should we use? With the lack of creativity, we go for x. All right, we use x for the entire state, right? That's another good idea to use x. Help me out. That's worse. X hat is worse than x. How about some a? Whatever is the mean value, whatever is the mean value of the prior you want to set. 0, it can be 0. In the SLAM problem, it's 0, right? So I'm just going to fix this and, yeah, Matt? Yes.
Can you say again what A or X in the previous line represents again? It seems like you said that it was a measurement, but it seems like it's the state that we're trying to estimate.
This is the state.
True state, right?
Well, there is a true state, but this is the state that we want to estimate given measurements, z and some prior. Prior is just to anchor the graph. It can be 0 unless for a particular problem you have some sort of knowledge about it.
So x0 is the prior, and x with no subscripts
Yeah.
is the state.
Now, x0 is a variable, but we place a prior to essentially make it noun. When you set 0 with a tiny covariance as a prior, you're really saying to the optimizer that don't change this much. Maybe it changes from 0 a little bit, but if the covariance is really tight, it's not going to change much. So that will anchor the graph, make the problem well-defined. Otherwise, again, we have the same problem of everything is relative. So it's not measurement in that sense, but it could be. Maybe it is coming from another source of information. So there's no, framework-wise, there's no limitation. In practice, we make it noun by an arbitrary value.
Okay, so my question then is, x with no subscripts is the state that we're trying to optimize over, right?
Right, x with no subscript was basically the entire trajectory. So the state is the entire trajectory, and by trajectory, I mean it can be at any time step position, orientation, velocity, bias terms, landmarks, anything we want to estimate. And of course, we assume we have enough information to estimate all of that. You can't just arbitrarily add state variables if we don't inject enough information or factors into the graph. So that's the story of factor graphs and least squares of SLAM. So this is a recurring theme in literature. There are tons of papers and problems. This is the framework you see. Once you understand this, reading these papers is very easy. In fact, you can skip that part. You can just go to what is the single novel idea that you want to talk about. Whether that's overwhelming or underwhelming, then you can judge the paper to be good or not.
Could you again repeat what A is?
A is some noun fixed value for the prior. 0, you can set it to 0. In your homework 7, you set it to 0, right?
I see.
Yeah.
It's an anchor for the distribution. It's an anchor for the graph distribution.
Yes, it's a value that anchors the graph. Forces x0. Basically, you're saying that keep x0 within this confidence of sigma 0 around this value, A. And tighter you make this sigma, the less you allow the optimization to explore other possibilities, right?
So is A like an initial guess of x0?
It is. Prior is initial guess, because after optimization, it won't be exactly A, probably.
I'm confused because you said that A is like a known initial guess, but we just used A to replace X with no subscripts, which we also just said was the state variables that we're optimizing for. So it can't be known.
Well, that was a mistake. I shouldn't have used X, because X was the trajectory.
Okay.
That was a notation mistake.
Oh, okay.
I fixed it by replacing X with some other letter, such as A. So maybe I write a remark here. A is the mean prior in many problems. Example, homework 7. We can set A equal to 0. 0 for pose means identity for the rotation, and 0 for the position.
And also be the global coordinate system. We want something to get different.
It is. The question is this the global or some reference frame? It is exactly that. If there is no knowledge, the global, the inertial frame is 0, is wherever we start. If you do have a knowledge that, for example, you want to work with north, east, down from a magnetometer, or some sort of reference that you prefer to use that, then you do want to force that to be your reference frame. Because everything else needs to be estimated relative to that frame now. A rotation of 30 degrees about z or x, right, might become 60 degrees because for whatever reason your initial frame is different. But the relative relationship remains the same. That's the beauty of it. The factors describe the relative constraint. No matter what you choose, the relative information is the same. Okay. So now we're going to go into, this was the general framework. Now we're going to go over an example that we can also construct the least squares problem, the linear system, the Jacobian, and see why the matrix, the Jacobian, ends up being a sparse. That's the goal. I'm going to use a simple example. The variables are dummy. It's like a single variate factor. But that will already shows you why it's like that. The higher dimension the problem has, the sparsity will grow, but you get a lot more zeros. So that's the idea. And that's a good thing, right? The number of non-zeros does not grow exponentially with the dimension or the factors we add to the graph. All right, so now we're going to look into the example. As if we are given a graph, we want to solve this problem using least square inference or estimation. Let me draw the graph. We have a factor graph. X0, X1, X2, and X3. And I'm going to add a loop closure that connect x3 to my initial variable. So we're dealing with a mini low-dimensional SLAM problem here. So the factors are a prior factor. We have a factor between node 0 and 1. We have another factor between 1 and 2, another between 2 and 3, and another factor between node 0 and 3. The fact that I'm using phi, that means all of them are the same type. I'm not changing the notation. That means this is the same type of measurement model. For example, it's a pose graph that we had. All of these models are relative poses. So let's make our way up to the least squares problem first. I do have x hat here, but it's x0 hat. That's a good, probably, way of defining the mean. Should we go back and fix it? That's an example of smoothing. This is the mean value of the distribution. You were right. I thought you were saying about x hat no subscript.
I was thinking mu or...
Mu would work too. When you stand here, you usually lose something like 70% of your knowledge and creativity. That's a fact. I highly recommend you trying teaching. We should fix here, right? All right. Happy? So what are the models? We made it clear already that these models are, for us, Gaussian distributions, exponential factors. So the prior is exponential of 1/2 of negative of. Now it doesn't matter it's x0 hat minus x0 or the other way around because it's a norm. Which is proportional to the probability distribution. We're going to use, now I'm making it more specific. These are the specific models. It's not F or H. My models are linear. So my transition model is between any node ij, because I am also describing phi 0, 3, is xj minus xi minus uij. So there is an input that when we add it to xi, it will give us xj. That's the model. And this is proportional to a model that describes the transition from xi to xj given uij. right? So you could imagine we had maybe some measurements, and then we processed that to get a relative pose between x0 prior and x3. And I is smaller than j, because that's what we see in the graph. So my xj equals f of xi and uij plus some noise and the noise distributed according to a zero mean wide Gaussian noise with covariance sigma ij. The residual that we can define is the difference between two sides of this equality. In other words, when you isolate the noise, what's left the other side, that's your residual. Because you want it to be zero. If it's not, that's the error we want to minimize. So xj minus f of xi and uij What's the next step? We're going to write the map problem. So the maximum a posteriori problem is done by minimizing the negative log of the joint distribution . Now this sigma is sum, the other one is the covariance. Again, probably it's better to use a different notation. Let's change this to, how about capital W? If you're taking note, you hate me because you have to go back and change it. That's why I never take notes myself. That solves the problem. Wait to see how things will roll out. And then at some point I'll make my mind what to write. All right, so the point is that this sigma here is the summation notation. Please do not get confused with the covariance. All right. So we already learned how to convert this into an unweighted version, which will be 1/2 of Cholesky factor inverse of the weight matrix. And for the other one, also the Cholesky factor, inverse of the Cholesky factor of the covariance matrix Wij. And now the norms are not weighted. These are just Euclidean norms. So we define this to be one half of some prior residual plus sum of all ij residuals. Or you could just write one half of sum over all, and this is k, and k here is 0, 0, 1, 1, 2, 2, 3, and 0, 3. So there's a need for tracking these indices in a key variable. That's why in GTSM you have keys. That's a map data structure that maps, it's a hash table that maps between variables and these indices. Quite painful to track, but once it's automated in a library, it's nice to just use it. And then this will be a least squares problem. So the map problem is, the solution to the map problem is by minimizing this quadratic cost function that we can solve. We know it's a least squares problem. So this is the art, right? We had a general problem under certain assumptions. We reduced it to a problem that we can efficiently solve it using a local solver. It is a local solver. You experienced that in your homework. If the initialization is not good, the solver can only do so much for you. So it's important to have good initialization, not just for one variable, for the entire trajectory, for all the variables, because the variable is not just x0 or xk. It's every state at every time step that we are considering in this problem. We have to initialize all of them. So what's the next step? Once you have a least squares problem, nonlinear least squares problem, what's the next step?
Step to the Cholesky factorization. Did we just convert to rid of these squares and then set their equivalent, or how did we get there?
So the question is, how do we convert the weighted least squares to unweighted? That was the remark I made here. You could work with the weighted least squares. I find it easier to convert it to bring the weight inside the residual. Makes it cleaner. And then once you're processing individual terms, you just compute the Cholesky factors, and then you weight them before assembling the Jacobian. So once you have a nonlinear least squares problem, the next step is to linearize it. because once we linearize it, we can solve the linear subproblem in Gauss-Newton. And for that, we need the Jacobian and the right-hand side of the linear system, because then that will lead to the normal equations. So we continue in our example, and now we're going to derive the Jacobian. So we don't linearize the quadratic term because it's least squares. We linearize the residual, right? We go ahead and write down the residual for the prior is L inverse times x minus its mean. So if it's not weighted, it's just the identity, but if it's weighted, the weight matrix is the derivative. For other factors, we have Lij inverse times xj minus xi minus uij. Now, because xj and xi are both variables, we have to talk about the derivative with respect to xi and the derivative with respect to xj. It's not just one variable. So the derivative of this residual with respect to the first variable xi is negative of L inverse ij, and the derivative with respect to the second variable xj is the positive of L inverse ij. Also, it will make it easier later to assemble this in a matrix form. So it's the same thing. This will make it easier to construct the Jacobian.
When we were initially talking about the formulation for the prior, for example, where we have x hat and x, we said that the order doesn't matter because it's in the norm. So it doesn't matter if you have one subtracting the other.
Mm-hmm.
When we start linearizing, the order doesn't matter, I guess, the questions, because then the Jacobian is negative L0.
Aliens don't like your question. This is a sign from God.
So if we have this,
Right, so you get a negative sign difference in the Jacobian, but in the right-hand side, you also have a different sign. So as long as you keep it consistent, it's fine. Yes, you will change the sign, but also the residual have a different sign. Right? You get sign change on both sides of normal equations. So it doesn't matter as long as you don't change it halfway through. Which is a message in everything we do here. Stick to something and then keep it consistent throughout the process.
So is there necessary to put the uij into the xi and xj vector? Is it necessary or?
Well, uij is measurement. It's sort of a given value. It will be the right-hand side of the equation. It's not my variable. That's why, yes, you could make this vector longer. The reason I'm doing it because it will come handy later. Otherwise, you have to think too hard how to assemble the Jacobian. You'll see now, right? There's no particular reason than helping us to know how to place the terms inside the Jacobian matrix.
Is it going to be a scalable?
In this example, you can think of these as a scalar, but they could be vectors too. You could think of them as vectors of any dimension. That's why I'm writing it in matrix form, L inverse, and keeping the order as if they're matrices. Basically, this is an Rn example. It's not a Lie group. Once you master this, the next step is, well, these Jacobians are a little more complicated because I have to linearize using exponential function and variables that are in the Lie algebra, right? But that's a whole different story that we covered it on least squares and Lie group. So we want to assemble A x equals B. I write it 5 by 4, but of course this could be blockwise. If these are not scalars, right? 5 is 5 blocks, and 4 is 4 blocks depending on the dimension of each variable. If it's 3D position, x0 has 3 columns itself. If it's a 6D pose, 3D pose, it has 6 columns. So it's a simple example. There's already a lot of structure to learn from this Jacobian. Do you notice any pattern? The matrix is sparse. There are a lot of zeros. These zeros are exactly the edges or factors that are not available between variables. x1 is not connected to x2 and x3 in the second row, right? In the second row, for example, this is one of the factors. So factors are rows. These are observations. Variables are columns. This is a Jacobian. In second row, that's one of the factors that we see. This is a factor that connects x1 to x0. Any other variable that is not in the factor will get 0 because the derivative is 0 with respect to those variables. If you have many more variables, these zeros will be very long. So that this matrix will be always sparse because the graph is not fully connected. Okay? And it's never be fully connected because there's just so many variables, not everything with everything is connected across time. The prior factor is a type of factor that provide information solely for one variable. The first row is only saying that directly what is the value of x0, which is the mean value. So that's just the equality that is telling you the value of x0 is x hat 0. The last column, that is row, that's the loop closure factor. In the loop closure, unlike the other factors, factor 2, 3, and 4, which has a staircase-like pattern, so any motion model is connecting two consecutive variables, which one of them is negative, one of them is positive, with some whatever Jacobian or coefficient they might have. So this structure will repeat itself. And especially if it's the same model, this is a repeating block for the Jacobian of the motion model or that factor. So assembling this large Jacobian is also modular. Once you know the models, we can just fill in based on this pattern. The last row is a connection between the first variable and the last variable. Anything else in between is 0. So it's a different type of pattern we see. So loop closures will cause fill-in in the Jacobian for variables that are not next to each other. Now, if the problem, in this case, is linear, in this example, if the problem is truly linear, this is the linear algebra view of exactly the same graph. Under the assumption that the noise was Gaussian, this matrix and linear algebra is equivalent of that graphical model. So they're the same thing, right? But if it's nonlinear, this is a local representation of that because we linearize.
Sorry, I don't think I quite caught that. So are you saying that because it's a linear system, this structure will look the exact same as if we had modeled it with a dynamic Bayesian network?
So this example, we're going through a particular example here. The models are linear. The Jacobians are all constant. If the covariances are constant, the Cholesky factors are constant. So A is a fixed matrix. If the motion model or the factors here would be nonlinear, we had to reevaluate the Jacobian at every iteration, right? So in particular, this is a linear least squares problem. It's not nonlinear, to keep it simple as a toy problem. Now, if the factors are linear, so the factor graph or the graphical model of any form we had, it is equivalent of solving a linear system of equations, which is nice. We know how to do it. Algebra is the way to solve the problem, right? We know exactly how to do it, and very efficiently. Under the assumption, again, the factors are exponential factors, Gaussian factors. If the factors are nonlinear, this algebraic representation as linear system is just a local representation of that factor graph based on current guess we have for the trajectory, right?
I guess also, like, actually, I guess if the system was linear too, even if the noise is multiplicative, we could also, like, do we also say that, like, like this same model holds, and if we're sticking to Gaussian, it's still Gaussian when it comes out.
So your question is, what if the noise is multiplicative? Well, we chose to model the noise as additive exactly because it simplifies the problem like this. That would make it more complicated, right? Because then, obviously, there's a need for linearization if the noise is multiplicative. So this is a nicest case, as good as it gets.
I want to ask if we have a loop closure factor, is there any chance that I can connect with multiple variable, or is just
You can. If the loop closure or any factor is connecting 3 variables, then 3 of these columns will be non-zero.
we're still calculating the Jacobian number?
Yeah, so any variable that exists in the factor will have a derivative. If not, then you get 0. And the factors are local, right? I mean, even a factor that is connecting 3 variables is somewhat rare in the literature. You can have it, but it's typically binary and unary. So because of that, for every row, you get non-zero for the columns of those 2 variables, or if it's a prior, just 1 variable, and everything else is 0, and that makes it super sparse, which makes it super fast to solve. So this is a sparse. So if we do sparse QR, so you do not want to use a generic factorization because that generic library will ruin the sparsity, will treat zeros as any real number. You won't gain any performance. So if we use a sparse factorization library, then A equals QR, Q AX equals QRX equals B, Q transpose QRX equals Q transpose B, solve via, this is an R is an upper triangular matrix via back substitution. So that's how we solve a SLAM using a least squares solver. So in GTSAM, what you're going through in your homework 7, we build the graph given data. So we do not implement the solver because it is already implemented. And you have a range of solvers to choose. And it will do least squares, nonlinear least squares and Lie group for you. Once you get familiar with the library, you can change different settings to do different ways of integration, but it is nice to have something like this because your focus is on building the graph. And this whole process of building the graph and solving it is the back end. If you remember, the front end was the messy part. You have to process all the data and then come up with these factors and measurements. Once you have all of them, you just construct the graph and solve it. So that's the story of graph SLAM and how we solve the problem. That's the end of lecture for SLAM.